Hey everybody, in this next video lesson, we're going to talk about how intermolecular forces affect melting and boiling points of substances. States of matter exist because of intermolecular forces. If intermolecular forces didn't exist, then everything would just exist as a gas. But solids and liquids are here and exist. You and I, the water we're drinking, they all exist because molecules will attract other molecules in one form or another. So in other words, without intermolecular forces, everything would just be a gas. So how does intermolecular forces affect melting points and boiling points? Let's take a look at this picture down here. We've got butane, propanal, and propanol. Now each one of these has intermolecular forces. The one on the top exhibits only London dispersion or dispersion forces. It has a boiling point of 0 degrees Celsius, where propanal has dipole-dipole interactions, slightly stronger, and the boiling point increases as a result. And then propanol has hydrogen bonding and has the highest boiling point of all of them. Now it's important to note that all of these are roughly the same mass, and so the only difference is the increasing strength of intermolecular forces and the increasing boiling point. Now on the other hand, what happens if all of your intermolecular forces are the same? Methane, ethane, propane, and butane all have London dispersion, but you can see that their boiling points actually get warmer as the substance gains in mass. This is a concept known as polarizability. In other words, the larger the mass, the more a molecule can become stronger in its intermolecular forces, because not all London dispersion forces are the same. Some London dispersion forces are weak. The weakest London dispersion forces happen with the lowest mass. But as the mass increases, the London dispersion forces and the strength of them increase, and as they increase, the boiling point gets warmer. So in summary, melting and boiling points are affected by the strength of the intermolecular forces and also the mass. We only really look at the mass if the intermolecular forces that you're comparing are identical. I'd like to further illustrate this point by taking a look at this graph. What you see here, if we start down here with carbon, is that each of these elements are all in the same group, and so in other words, what's happening is as you go down a period, and that's what this is down here, we're going down a period, we're increasing in period along the same group. So carbon is above silicon, is above germanium, is above tin. What you'll notice is that the boiling point gets warmer because the mass increases as we go down a group. And this is true in this column. This is group 14 where carbon, silicon, germanium, and tin are. Now you'll also notice as we move one to the right, now we have nitrogen, phosphorus, arsenic, and antimony. And so we've got the next group. Well, this one, you would expect NH3 to actually be down below pH3 because it has the lowest mass of them all. But NH3 exhibits hydrogen bonding. And hydrogen bonding is the strongest of all types of intermolecular forces. And so that means that the boiling point is higher. But without hydrogen bonding, nitrogen would be somewhere down here around -100. It would follow this trend of increasing the boiling point as size increases. You can see it here for fluorine. These are all the halogens. You got fluorine in period 2, chlorine in period 3, you got bromine in period 4, and iodine in period 5. You see a general increase as the mass increases from chlorine to bromine to iodine, but you notice fluorine kind of is not in the right spot. Because if we draw that line kind of diagonally down to the left, fluorine would be somewhere down here, about -100, maybe a little higher. Hydrogen, when it's attached to oxygen, is polar and exhibits hydrogen bonding as well. And so we've got group 16, which is oxygen and sulfur and selenium and tellurium, all bonded to 2 hydrogens. And the trend is pretty consistent with sulfur, selenium, and tellurium. Those are getting heavier, so you can see that their mass increases and their boiling point increases. And if water was following this trend, it would be somewhere between -50 and -100, but it certainly is not. It boils at +100 degrees Celsius. It's because it has hydrogen bonding. So these 3 are outliers in the normal trend, as you'd expect, because they have hydrogen bonding, where the other elements that also are bonded to hydrogen do not exhibit hydrogen bonding. Well, that takes care of this video lesson on how intermolecular forces affect melting points and boiling points. Thanks for watching.